Hey everybody, how's it going? My name is Ali. Today I'm going to be talking to you guys about my senior thesis. What was it on, you ask? Well, nothing but a simple little thing I like to call automated measure extraction using self-similarity and dynamic time warping. What does all that mean, you ask? Well, let's break that down real quick. But first, I want to go over the fact that this is considered a project in the broader topic of
computational musicology.
Computational musicology is any kind of work that uses computer science to solve problems in musicology, or in other words, the study of music. The particular subtopic in computational musicology I've been working on is called Music Information Retrieval, or MIR for short. MIR has to do with the extracting of data from music. If you weren't already aware, music is encoded on computers by using something called samples, which are basically numbers in a row. These numbers represent the height of what we call a waveform, which is a visual representation of a sound wave. You can kind of see here how a whole bunch of these samples can eventually be combined to represent an entire piece of music, which is the basis of how my project was possible. Another important feature in music is what's called the measure. As you can see here, a measure is basically a unit of music. Right now we're using Happy Birthday as a really simple example for this. We divide the music into measures, so when I hover over one of these and it turns red, that's a measure. Here's what one measure in Happy Birthday sounds like. Yep, that's it. The problem I was set to solve was to figure out how to use digital recordings of music, in my case I used Mozart sonatas, to automatically divide this music into its own measures. I used classical music in the interest of this problem because classical performances are more likely to have variances in the measure length due to the nature of how it's composed and performed. The benefits of having the ability to do this are that future researchers and musicians alike will be able to just pick out a measure that they need to listen to for whatever purpose they have, rather than listening through an entire song, and still be able to get the quality of a live performance. I already knew that as a point of reference I could use sheet music, and what better way to do that than to use MIT's own Music21, a Python library that encodes sheet music data, which just so happens to let us also analyze this data measure by measure. But what of the audio? Don't I still need to slice that up? Well, to do that, I went ahead and turned to a 1999 classic called Visualizing Music and Audio Using Self-Similarity by Jonathan Foote. Foote's research basically looks into the use of self-similarity and short-time Fourier transforms to determine how similar two pieces of music are. Basically, Fourier transforms are a way to unwrap individual frequencies, and self-similarity lets you see how similar two pieces of audio's frequency are to each other by measuring something called their cosine distance. These days, we have Python libraries for that, which is why I turned to Librosa. Librosa is a Python library designed for wrangling problems involving music information retrieval, and one of its prime functions is the ability to extract the samples that you need out of music files. The other great thing it does is it lets you perform the kind of self-similarity that we saw in Foote's research. When you plug in the data from two sources of the same audio, you can output it in all kinds of ways. One of which is this graph right here. What's so special is that by converting the distances onto a plot in a Cartesian plane, we get a function of the dynamic time warping between audio A and audio B. In other words, we have a graph of how much faster or slower our MIDI is than our recording, based on whether it dips above or below the ideal slope of y equals x. And even luckier for us, Librosa gives us access to these slopes. But what do you do with them? To solve this, I first had to convert my Music21 files into MIDI, and then I had to get the MIDI representations of every measure in each Mozart sonata that I was going to analyze. First, I would grab any given measure of MIDI. Let's call it M. For each M, we can figure out what percentage of M is in the entire MIDI file. That's the same percentage of slopes we'll be grabbing from our entire list of slopes from earlier. Let's call this percentage P. If we take the average of these slopes, we get the average difference in time between our MIDI and our audio. By applying these averages as a coefficient to the number of samples in our MIDI, we get a new index for where the endpoint of our measure in the recording is. And because the process is iterative, we can start with 0, and each start point after that will be the index after the last endpoint. After that, it's a matter of exporting the samples and reorganizing them to taste. The real question that you guys want to know is, how did they sound after the fact? Here are a couple of my favorite clips. And a couple of not-so favorites. I ended up finding that there was a definite relationship between how good my inputs were and how good my results were. For example, if I had recordings that had a lot of trailing and ending silence in them, or if I had MIDI files that when I exported them measure by measure ended up creating empty measures, or measures with extra silence that was unnecessary, it would end up skewing the eventual results. I tried my hand at some data cleaning by getting rid of some of the extraneous data, and it helped a little bit in a lot of cases. In the future, I think trying to find new input data by finding new ways to get some of this MIDI data, or by finding new recordings by different performers, we can definitely change the fate of some of the more negative results. At the end of the day, I think that the algorithm proved that it could do its job, which I think is a pretty awesome thing. I want to thank Dr. Watkins for being a great mentor during this project and for working with me every time I told him I messed up something new. I also want to thank Dr. Nairn for coming up with part of this research with Dr. Watkins. If it weren't for the two of them pulling me into their FSC a couple years back, I wouldn't have been able to do any of this or learn any of the things that I did. Additionally, thank you to all of the math and computer science faculty who helped give me such a great experience here at BW and helped me get to the place where I am today. Have a great day.